Thanks everybody for joining. My name is Joe Breher. I'm with Western Digital. I'm a standards wonk. And I'm here to talk to you today about a new feature in both SCSI and ATA known as repurposing depopulation. What this feature is about, in essence, we all realize that all systems fail at some point in time, right? I'm going to talk in terms of various storage devices, but what the core feature here is if we have a device that has some sort of failure, some sort of degradation, but that failure or degradation is limited to some subset of the device, how we can use the remainder of the device as a fully performant device and sort of ignore the pieces that aren't working. So as far as an agenda here, I'm going to talk a little bit in more detail about what problem it is we're trying to solve here. Talk about some of the building blocks that go into building a solution for this problem. And then we'll talk about, at the interface, what has to happen in terms of protocol flows in order for this feature to be employed. And we'll look at industry standard implementations. Again, as I mentioned, both T10, the SCSI committee, and T13, the ATA committee, have incorporated this feature in the recent version of their standards. We'll look at how a host might make use of this feature, and then talk about what some future developments in this area might be. So before I really delve into it, I want to point out that this feature has been developed with pretty broad participation across multiple standards committees. I mentioned both T10 and T13. It's been advanced mostly by a coalition of Seagate, Toshiba, and Western Digital. I was the lead editor on this feature, but worked closely with some peers in Seagate and Toshiba. And the feature itself, we've tried to abstract it to be technology neutral, although the initial implementations are in hard disk drives, and I'm going to talk in terms of hard disk drives, but realize that other technologies have portions that might fail as well, maybe a flash die or channel or something. And we've tried to abstract it such that it might be applicable to things such as that as well. And there is now a standardized implementation. I've said that, I guess that's the third time I've said that, but it replaces some earlier proprietary protocols to do this same sort of thing that have existed from a number of vendors and have had some use over the last several years. So, as far as what the problem is, device reliability today is pretty good. I mean, you know, your warranties are 2 million hours or 3 million hours or something like that. That's a pretty long time for a mechanical subsystem. So that's a large but limited lifetime, right? I mean, at the end, in the end, all mechanical systems or electrical systems as well, subject to wear out at the gate level, have a limited lifetime. And what we're finding is that, or we've known for some time, the different subcomponents of storage device wear out at different rates. So again, what we're trying to do here is to, once a portion, well, I've illustrated this here with we've got a disk stack and some heads there. We've got one actuator, one head that's labeled as red. What happens if that surface goes bad, or that head starts degrading, or the channel that head is attached to, the analog characteristics start drifting such that you're getting excessive latencies to any access directed at that particular head? You know, if your system latency is going down because 6% of the drive has a problem, then perhaps it might be a good idea to cast that 6% of the drive out of the population that you're using and use the rest at full performance. Now, just in terms of disks, in the past, we'd tend to see more systemic failures, right? A disk would tend to fail in the electronics as a whole, or it might be a debris-caused issue that would propagate across multiple heads, surfaces, whatever. As time goes by, however, we're finding that certainly the debris problem is going down. And the systemic failures are a smaller portion of everything, so that we're getting more situations where a degradation or a failure might be limited to a head or a surface and not propagate against the rest for a good several years after the event, causing the damage or degradation to the one head. So what we want to do is capitalize on that remaining service life, past the 2 years or 5 years or whatever it ends up being, another 2 or 5 years, and employ 97% of the drive after that. So one of the things that complicates this, the solution to this problem, is that in the past we used to have essentially fixed relationship between your logical block space and which physical elements in the drive are going to map to that logical block. However, that's no longer the case for many drives, and the proportion of drives that are doing truly indirected LBA logical to physical mapping is growing as time goes by. So that's one of the things that complicates the solution here, although it hasn't made things too difficult. So again, the central value proposition of the depopulation feature is to offline a degraded element, a portion of a drive, while the other elements remain in service. So some of the building blocks involved in this solution for this problem here are that as the drive is operating, it's continually monitoring its performance, maintaining, through thresholding on ECC rates and whatnot. It'll continually compare its performance per physical element, per surface, against a standard. If indeed a threshold is crossed in any performance aspect for a given head, the drive will send a semi-asynchronous signal to the host indicating that this event has occurred. I say semi-asynchronous, it's as close to asynchronous as SCSI or ATA can accommodate today, because they don't truly accommodate asynchronous operations. But what this essentially boils down to is on any I/O command, the drive would return a informational exception on SCSI or a device statistics notification on ATA indicating, hey, physical element status has changed, at which point that's a signal to the host to issue a query to the device. There's new commands in both SCSI and ATA called get physical element status. And we'll look at this in detail in a moment, but what this does is it returns a physical element health value for each physical element in the device. Again, a physical element being an abstracted representation of, in the hard drive case, or at least in our implementation's case, as a head or surface. And then if the physical element health, there's a normalized value, that's a normalized data quantity. So once the get physical element status data is returned to the host parses it. It can see if there's any outliers in terms of the value of the get physical element or the physical element health status. And if there is an outlier, that would indicate that that is a bad physical element. In which case the host can, at that point, command the device to remove an element with the remove element and truncate command. I guess, again, this is a new command that's added to both SCSI and ATA. So, upon receiving the remove element and truncate command, the drive goes through a number of processes, but essentially what happens is the physical element that is specified with the identifier in the remove element and truncate command is removed. In other words, it becomes ineligible for storing any data. And this is actually a reduction of physical capacity. Following that, the device logical capacity is truncated and that's to reduce the logical capacity by the lost physical capacity, such that the resultant logical capacity is sufficient for, the logical capacity matches the physical capacity. So in practical terms, that means that the last LBA, such that would be returned by read capacity, would be reduced to a smaller value. Yes?
So if that happens, though, would the data be expected to still be readable from the drive?
Well, no.
Because I would imagine you'd lose it.
So we'll get into that a little bit more in depth in a bit. The initial proposal was for when I first tried to start standardizing this, I initially came in with what I called online logical depopulation, right? Which, let's just defer that.
You just can see all sorts of problems with this.
Well, yeah, there are, right? I mean, you get holes moving around, and yeah, we'll go there. But,
Right.
all right. So, and then following the element removal and the logical truncation, the device may engage in an optional initialization. And some implementations don't need it, but other implementations, the format embeds the logical block address in each of the physical elements, each physical storage location. So in that case, the reinitialization would be required. So that's device option, and that's advertised. There's a time for the device advertises the time for this process to occur. So as the result of a depopulation, essentially what happens is the device returns as a new, smaller, good device. So essentially the host assumption has to be that all the data is gone, right? It's all data on the disk has been lost. It might actually still be there. I mean, that's not required that it be eliminated. So if security is a consideration, then it's a host responsibility to do whatever sort of sanitization it might deem necessary. So the scenario is, essentially, logically, it's replacing the drive with a smaller drive, but a drive that's in good state. And this is useful in the case where, there are certain environments where it's very expensive to replace a drive. You want to keep as much capacity online as you can, but it's not worth sending a tech in to actually pull and replace. So with that as preface, we'll take a look at the protocol flows here. That's actually a pretty simple protocol. So in essence, the host might be, let me see, can I get yeah. So if this arrow here is really just a sequence of read and write operations, right? As these read and write operations are occurring, the drive is continually monitoring its performance and the physical element status, internal physical element status. At some point, if, there's my, at some point, maybe an ECC threshold is crossed, or the drive detects a scratch, or a head suddenly, maybe it's a hammerhead or something that is past its lifetime or whatever. If there's a problem that the device detects a physical element threshold cross, as a result of sending status for one of these I/O commands, it will send an informational exception. The particular informational exception is warning physical element change. That's a signal then to the host that it probably wants to issue a get physical element status command. And we'll look, shortly we'll look into what this CDB actually looks like. So when the device receives get physical element status command, it goes and builds a parameter data structure which provides, in addition to some other statistics, physical element health, normalized value for each physical element, and returns that to the host. So then once the host receives that data, it'll parse it, look for any outliers, and then if it finds an outlier in that same parameter, will be a physical element identifier that it can use to plug into the remove element and truncate command to issue to the drive. And the drive then would remove the element from remove the physical element from physical inventory, truncate the logical capacity, and then perhaps engage in a format command, or format operation, sorry. So is that clear so far? Questions? Cool. All right, so from the drive's perspective, the command processing for a remove element and truncate command, the drive optionally can execute these as background processes. It might be handled as a foreground command, it might be handled as a background command. But there are three distinct phases of the command processing. There's a depopulate operation, which again reduces the physical capacity by casting out one physical element from the usable inventory. It performs a truncate operation, which is a logical reduction in capacity, or a reduction in logical capacity, and then an optional initialization function format. During the time when these operations are in process, there's a very limited list of commands that are allowable to be processed. If indeed this command ended up being processed as a background operation, it had return status for the command already, and then went ahead and did the depopulation, truncation, and initialization, then of course the drive is free to process other commands. However, that set's limited to essentially queries. Inquiry, mode sense, and get physical element status. And indeed, get physical element status returns an indication that if there is a depopulation currently underway, it identifies the physical element that is currently being depopulated. So the host can poll for completion. How does the host know when to poll for completion, if indeed it's a background operation? Well, the device has already advertised a depopulation time. It provides that in a VPD page on SCSI or in the identified device data log on ATA. So, as I said, there's a couple of industry standard implementations. T10 has incorporated this into SBC4 last November. The current version right now is SBC4 R14. If you pull a presentation, this is actually a live link to it on the T10 website. And then T13 has incorporated it into ACS4, the ATA command set, version 4, in February of this year. So let's look at, let's pause here for a second. Any questions so far on any of this? Clear as mud. Yes?
It feels to me like this would require all new controllers, or at least new firmware on controllers, to take advantage of. So it's kind of a clean slate from a hardware perspective. Is that reasonable?
Yes. So early customers that are taking this have a management layer and are in control of their applications and whatnot. So there's a management layer over a slab allocator or whatever. And this management layer already deals with logical capacity coming and going, right? So it has the ability to say, well, I'm going to take this logical capacity offline, issue these series of commands, bring it back into the pool, and do allocation of new constructs over it. So yeah, I mean, there's obviously host side stuff that has to happen.
So maybe as you were telling me that, I realized I might have been wrong. Is it purely software implementation, or is there a dependency in the drive controller, whether it's a SCSI controller or an ATA controller, to handle the updated command sets?
Well, okay, so it's abstracted such that the actual management layer itself can be common to both ATA and SCSI. However, the actual implementation, I mean, obviously the SCSI has CDBs and ATA has their command formats, right? They're not identical. So am I going down the right path, or I'm not answering your question?
So I've got a 10-year-old server in my home lab that's got a 10-year-old SCSI controller. Can I take advantage of this technology if my OS supports it, even with that 10-year-old SCSI controller that obviously doesn't?
Well, 10 years, most 10-year-old, well, I'm thinking, yeah, so there is a SCSI pass-through command, right? Most controllers support being able to send arbitrary CDBs out the HBA, right? So yes, in that case. It's usable on HCI, for instance. It's not like you need new hardware on the host end to do this.
Okay.
Is that where you're going?
Yeah.
Okay. All right.
If it's purely at the software, the OS, the driver level,
Yeah.
and it's dependent on specific support from the controllers or from the drives themselves, beyond the existing query structures.
Right. That's correct. All right, so let's switch gears a little bit and look deeper into how this looks on one of the implementations. I'm just going to go with SCSI, but ATA has similar constructs. In the SCSI SBC4 standard, section 4.38 is the model describing repurposing depopulation, essentially defining what dependencies it has on other features, what the processing of it looks like, the mechanism, notification, operations, and effects on other commands. 5.7 is the definition of the get physical element status command itself. 525 is remove element and truncate command definition. And then there is a new informational annex which sort of describes some of the considerations that a host might want to think about in order to employ this feature. So here's a look at the CDB for get physical element status. It's got the normal, it's got an opcode and a service action which define it as get physical element status command. It has a starting element and an allocation length which allow us to iterate across, well, let me back up a notch. So we've got a 32-bit space for starting element, right? So in the case of a disk, that seems kind of big. However, if we go as far as an SSD erase block or something like that, it might not be, right? So in the case where there are a lot of elements, it might make sense for the host to iterate through a larger list. And the starting element and allocation length allow that activity to happen. So by the host issuing a sequence of get physical element status commands, each with an incrementing starting element, they can iterate through a larger page. So the report type, it's kind of dormant today, but it specifies whether the report will return a list of all physical elements or only storage elements. And this is something I haven't touched on as of yet. This get physical element status command is abstracted in a way to allow for future extension to things other than storage elements. Today, we're only dealing with storage elements. So a storage element is something that can hold something that an LBA might map to. Yeah. And then there's a filter field which will specify whether the list that is returned contains all elements that match the report type field or only the interesting ones. And the interesting ones would be ones that have failed, ones that have already been depopulated, or ones that are currently in the process of being depopulated. We'll dive down a little bit deeper into that in a bit. So this is the data that's returned by the get physical element status command. We can see we've got first a header that's got a number of descriptors. This is the number of descriptors that the device would return if indeed the allocation length was big enough to return all descriptors that the device is capable of returning. It's got a number of descriptors returned, actually returned, in case the allocation length has constricted it. That would match that. In the case of ATA, everything's returned in 512 byte chunks, so you need to know how many of those actually contain valid data. There's the identifier of the element being depopulated, which of course, if there is no, it's valid if there is an element currently being depopulated, at which point this data is being returned. I guess now it would be a good time to tell you that by specification, 0 is a non-valid element identifier. So if that value is 0, that would indicate that no element is currently in the process of being depopulated. And then it follows with a bunch of these physical element status descriptors, each of which looks like this guy over here. So each one has an element identifier specifying the element being described. It's got a physical element type. In this case, it would be a storage element. Once again, we haven't defined other physical elements types. And then this physical element, the most interesting probably here is this physical element health parameter. And this is a normalized value indicating essentially the health of that particular physical element. Any value lower than 64 hex or 100 decimal is within the manufacturer's specification limit. Now, some manufacturers may choose to make that a scalar. Others might implement only a value, 1. Might just implement everything within the limit as a single value. But it can be a scalar. At 64 hex, it's right at the manufacturer's spec limit. So that's, if it got any worse, it would be considered bad, right? 65 through Charlie Fox would be outside the manufacturer's spec limit. Fox Dog would be a depopulation error. In other words, this physical element had previously been the target of a remove element and truncate command, which had failed. Fox Easy would be this element is currently in the process of being depopulated, and Fox would be this element has previously been successfully depopulated. And let's see, earlier we were talking about what in the filter field, what are the list of interesting elements, right? If we want to return a list that only contains the interesting ones, so we've got a smaller data set to look at to figure out if we have any problems that require addressing, then it would return anything from 65 hex to Fox hex for the physical element health value. It would not return any physical elements that match 64 hex or below. So once this data is parsed again, if the host finds an outlier here, say this is Charlie Fox here for the physical element health, it can match that up and say, oh, well, that's the element identifier of a failed element, so I want to depopulate that. It can issue a remove element and truncate command and put the element identifier, that same element identifier, in that remove element and truncate command. So that specifies the element to be removed, in which case the element would be removed, the logical capacity would be truncated, and an optional initialization. So there's one little wrinkle here in addition. There are some hosts that cannot deal with devices that are arbitrarily sized. The canonical example would be RAID devices. A lot of RAID systems expect all the devices in a given stripe set to be of the same capacity. So if indeed such a device has that limitation, such a host, mid-plane device has such a limitation, it can specify a requested capacity. And if the device, if the device receives a command that has a requested capacity in it, then after all the processing, the remove element and truncate, the optional initialization, the device will have that value as its logical capacity. Now, there's a good chance some devices might not support that. A device might not be able to accommodate that particular requested capacity. A value of 0 in that field indicates that the device gets to choose the resultant logical capacity, and we see that as, with our current customer base, we see that as the leading implementation. But if the device is unable to meet that requested capacity, it fails the command before beginning processing it. Now, a logical question is, well, how does the host know what capacity to request? And to answer that, we go back to our physical element descriptor data, and associated with this element, with each element identifier, is the associated capacity, and that is the amount of physical capacity reflected into the logical domain that this particular physical element is currently implementing. So the host then can subtract this associated capacity from the current capacity of the device, and it knows that that's an upper bound on what it can ask for in the requested capacity field. So does that all make sense? Cool. All right, so how does a host implement this? I mean, what are the things a host needs to look at to actually make use of this feature? Well, it's going to carry out its I/O operations while monitoring for an additional sense code of warning physical element status. And in the SCSI domain, this comes across as an informational exception, which SCSI has a rich set of behaviors that you can map informational exception to. A unit attention, a no sense, et cetera. That's all set up in the informational exceptions mode page. But on ATA, this is mapped to a device statistics notification. Again, there's a fairly rich set of behaviors that device statistics notification supply. So in essence, this is, as I said earlier, kind of a semi-asynchronous signal to the drive that something interesting has happened. So if it sees a warning physical element status change, then the host would, logically, it would probably want to issue a get physical element status command. Once it gets that data, it should parse that for any physical element health field outside the manufacturer's specification limit. And at which point it might find, well, use case dependent, if the host wants to save any data. I just want to drive home the fact that after this operation completes, all the data that was on the disk is not guaranteed to be there any longer. So if there is any desire to retain the data, it is before the remove element truncate command that you want to migrate that data off this particular disk onto some other store. At which point the host can issue a remove element and truncate command, and then once that process is complete, essentially the drive is logically, it's a new, somewhat smaller device. So just in flowchart form, this is essentially the same thing. No sense to belabor this. I guess the new element that's called out here is the sense code for the warning physical element status change is on here, 0B14. Okay. Well, any questions on that so far? No. Good. Clear. Excellent. So now we're going to come around and talk. Oh, and he's gone. we'll talk a little bit about what future stuff might happen. So as I was saying earlier, initially we came into committee with something we were calling online logical depop. So this is kind of a nice feature for people that are more interested in saving most of the capacity of the drive, and perhaps they've got data migration going on all the time, maybe it's an erasure coded system, whatever. The logical question now is, hey, well, if these other surfaces are okay, why are we throwing away the data that's on them? And why are we incurring the time it takes to do an initialization, right? Well, the problem that we have is if we just cast one physical element out of the population, you end up with a hole in the LBA space. And not only a hole, it is, in the case of an indirected drive, it's multiple holes, and not only are there lots of holes, but they move around in LBA space, right? So as you're writing and reading in an indirected system, those gaps they'll have a tendency to move around in LBA space. So that's, as we propose this, several significant customers said, you know what, this is all really cool, but what we really need is just a way to use most of the capacity of the drive. We don't care about the fact we're erasure coded anyhow. We don't care about the fact that, the capacity there, the data isn't there any longer because we're just, we've got a replicated copy. We'll just bring it back anyhow. And we don't want to make the complexity of online logical depop delay the introduction of this feature in a standardized manner. So that's kind of where we are today. However, if it becomes of interest to a larger population that is actually interested in all the complexity that goes along with it, we have defined and prototyped the online logical depop, which has mechanisms for addressing the migration of holes in the LBA space by adding an amputation and regeneration function. Various other queries to manage those holes. And as I said, we'll reintroduce that if there's customer pull for that. So, where are we today? Calls to action. If this looks interesting to you, if you want to save the capacity of the bulk of a drive after a small portion of it has gone bad or gone marginal, go ahead and implement this in your host storage stack. You have several vendors that have the same outward protocol compliant implementation that you can choose from. Provide feedback on the utility and the design of this through either the SCSI committee, T10.org, the ATA committee, T13.org, or hit me up directly. And again, if you desire a data preserving variant, let somebody know. So that's pretty much all I have. Any further questions? Yes?
So if you have like a bad head, why would the holes move around in terms of, if you won't write to a bad surface, you might write a block to a good surface, so it seems like holes might shrink or something, if you never have like a hole.
Well, so you're essentially removing some physical capacity while retaining the logical view across it, right? So if indeed the logical to physical mapping was contiguous, I mean, in the olden days it was, right? I mean, you had cylinders and sectors and cylinders and heads and sectors, and that was all knowable a priori, right? That's not the case any longer. Today, well, it was never completely the case because there was always the reallocation of bad blocks, but today, as time goes by, a larger and larger proportion of the drives that are shipping are fully indirected, right? So that it's at the point where a write occurs that mapping from logical space to physical space occurs. So once you've got a hole there, right, you've got that hole, but when you go to do another right, perhaps this sector over here wasn't used. You've got this hole over here, right? This sector over here has never been used. A right comes into what used to be mapped to this LBA, right? So now that's going to be directed to that LBA, okay? Now, at some point, you're going to run out of sectors that have never been written, right? So other sectors that get trimmed would be available to for further rights to come in, right? So that's where the possibility for the migration of those holes comes in. Does that make sense?
Trying to accept them, right? You'll never redirect to like the platter that had that head.
That's correct, yeah. But it's in LBA space where it's that mapping, the mapping moving around that is the sticky wicket.
You're going to shoot that holes in that LBA so that we can like rebuild the LBAs that we know are bad, like the 6% of the LBAs that we know are bad, and then build the rest of the LBAs later.
Indeed. So there were tools for that in the online logical depop set, right? And the low-hanging fruit from that is an extension of get LBA status, which returns that mapping to the host and has an indication of the bad ones and whatnot, right? So that's something that can be done without absorbing all the complexity of the larger feature. Anything else? Yes.
So there's no command in the spec that would, once you have actually removed an element, to bring it back online?
No, there is not. There's been a lot of discussion about whether that would be good or not. The customers that we had been talking to found no value in that. And it brings up, frankly, warranty implications, right? I mean, it gets complex when you start offlining things, bringing them back on, et cetera, et cetera. So, no, this is viewed as it's unidirectional.
I can only think of in terms of data recovery that might be, or even in terms of like, okay, I can still read from it, it's just degraded. I would like to kind of erase as much as I can before I destroy this drive or whatever. Those types of situations where
Again, so another extension that was in the online logical depop functionality set was get LBA mapping, right? Once one did the get physical element status, right, and found that element identifier X was bad, then one could issue get LBA mapping with the element identifier, and it would return the list of LBA ranges that are currently mapped to that element. Now, in order to make that work, you have to kind of quiesce the drive in the meantime. Otherwise, that mapping, again, that mapping's not deterministic a priori, so there's complications around that. But certainly we can go, if that's a useful feature to you, get your feedback to the SCSI committee or the ATA committee, or I'll take it back,
So you take, let's say, 10% of logical element offline, then if you bring 10% of the capacity, and then in turn drive for garbage collection and make everything intact.
Yeah, so if, that's one of the reasons why SSD has not been the early target for this, and it's been kind of a hard drive thing, is because SSDs already have a lot of over provisioning, right? So as a standard operation, right? They're doing fully indirected, but they've got so much capacity, they lose a die and they don't care, right? You lose a little bit of performance, but essentially undetectable from the host interface. So you don't have to issue something like this in that sort of environment.
But is it SSD can use this feature and say like I can guarantee lifetime performance, and they lose, then they can keep reducing the capacity and keep maintaining it.
That is correct, absolutely. Yeah, they can maintain an over-provisioning percentage past what they're they can.
I mean, if you're kind of managing your own logical
to, basically as you're managing your essentially you're replacing a lot of what might traditionally been done on the drive itself.
Yeah, within the FTL or whatever, yeah.
The FTL.
Yeah.
And so if you're implementing the software,
Yeah, certainly. Something like Open Channel or something similar to that, this idea could certainly have some applicability, yeah.
that said, you don't want to reformat like every cell, just one cell.
Right.
So you need to have some way to
Yeah, granted. And, there are systems that work with, I'm trying to think of the term. So fully provisioned. Well, there's a term for a device that advertises more thin provision. Thank you. That's it. A thin provision device, right? There are systems that already know how to deal with a thin provision device. In which case, you could implement something like this that didn't, that just all it did was cast out it removed the element, and that was it, right? Because if they already know how to deal with logical space that doesn't have physical backing, right? There's, then the problem's solved in that.
It's been written to, so have to get the data off.
Yeah.
That's the challenge. You need some kind of RAID within the drive or something like that to be able to, or some sort of erasure coding.
Yep.
I could see something like this being really useful in high-density Hadoop clusters, for example, where you're doing a bunch of 10 terabyte drives today, and you don't want to just throw the whole drive away, and you're okay, and your application, even above the storage layer, can handle losing a drive temporarily and bringing it back smaller.
This is obvious implications for Ceph, positive implications.
Yeah. Okay. Cool.
That's a natural use case because Ceph doesn't really care what its OSD size is. If an OSD goes away, you can bring the OSD back.
That's good feedback. Thank you. All right. Thanks.